right, it's 11:01. Let's go ahead and get started to make sure we have enough time. Welcome to today's webinar on internal threads and round internal undercuts. I'm really excited to talk to everyone about this, these options today. DME has a lot of options from one source, which really gives the customer a lot of information and able to address their barrier right for undercuts with multiple solutions, with one source. And not to mention, we have a really good engineering team behind us here where we can help you with consulting on your mold design and make sure that you're getting the right solution for your application. During the webinar, feel free to put some questions in the chat. On the right-hand side, you should have the availability to click on questions and type them in, and we'll try to get to them at the end of the presentation. So today, Mike Raymond, our Director of Engineering here at DME, will be talking about some options that we have for undercuts and threaded solutions. And then also the Chief Sales Officer for our partner Servomold, Richard Gain, will be here as well to discuss Servomold and what options he has available for you. So with that, we'll turn it over to Mike Raymond.
Okay, well, hi everybody. The first thing I want to do is show our video. So we're going to show you our latest DuraCore, which we launched last March, and we have a video to show you. So we'll play that, and then behind it, what we'll do is I have some samples of different ones we made.
Premium yet cost-effective solution for parts with internal threads and undercuts. Introducing the next generation of spring collapsible core, DuraCore, for internal threads and undercuts. Key features are avoid segments contact during motion, easy cleaning and maintenance, short safety ring, improved cooling, reduce mold base stack height. Key attributes are sequential opening, two-piece design, shorter safety ring, use of straight core pin, reduced collapsible core length. Benefits of two-piece design: effortless disassembly for easy inspection and cleaning with rapid, secure reassembly to minimize production downtime. Enhanced safety achieved through a shorter safety ring mounted securely on a safe plate. Optimize manufacturing and cooling efficiency with a straight core pin, leading to improved overall performance. Realize space-saving advantages with a reduced collapsible core length, effectively minimizing the mold base stack height. The space-efficient design accommodates more cavities, maximizing production output per cycle and boosting overall efficiency. DuraCores are available in round head or flush head forms. DuraCore advantages: during the mold closing phase, the large segments smoothly pave the way, allowing the small segments to follow suit. Small segments follow the large segments without contact. This ensures no additional load on the small segments during the mold closing phase. Large and small segments move without touching each other. This breakthrough minimizes wear and tear, enhancing durability of the DuraCore. Thank you.
Okay, so what we're going to do now is we're going to show you some sample parts here. So, okay, so this is our slide one. This is just a standard thread. The center drive pin is extended out past it through the top, so we could form a cutout in the center of the part. The thing about this one that is unique that I'm trying to show you is if you look at the picture on the right, what we did is we formed a part lightener that we attached to our safety ring. So we actually try to make these for the people, for the customers, because we want to get a nice fit through that. So this is the reason why I wanted to show you that. So if you have lighteners and you got to run some threads through it, we can accommodate that. Next slide, please. Okay, so there's a couple unique features on this one. As you can see, it's a 50 millimeter diameter. Anything over 40 millimeters, it does not require a safety ring. While manufacturing the core, we made the material lightener for the sidewalls. This way, everything's going to fit together during the manufacturing process. We want to make sure of that. The second thing we did, if you look inside the drive pin, we built spiral cooling in there so that we can get more cooling in there. On this one here, we could put something like this, anything over an inch on the drive pin. We could put spiral cooling into it. We put baffles into them sometimes, and on smaller ones, we use high flow cooling tubes. Next slide, please. I just want to show you on this one here that we extended the center drive pin, and then we ground the part form onto it. And you can see the red lines. That is the actual parting line that we go for, and I'll explain that to you in a few minutes here. Next slide, please. This is a part that's kind of unique. As you can see, we had to extend the center drive pin, and then we put a core pin in from the top so that we could finish, the cutout through it, and we created a taper interlock into it so that everything locks together and it maintains concentric throughout the part. And when we made this core pin, we had to put vents on the core pin because you can see how far that part goes up it'll go up into the cavity and it would trap air. So that's why we built the core pin with the vents on it. Next slide, please. This part just has a snap feature on it. And we ground the top of that drive pin to form a lightener into the part. Okay, so next slide, please. And this one here, there's a couple different diameter changes in it. As you can see underneath the threads, and then we extended the actual segments themselves and continued to form the part shape above the threads. Okay, so I'm going to show you one right here, the next one. Okay, so I wanted to show you this slide here because these are the most common problems that we find when people design their tools. When you design these parts into the mold, you got to make sure that that part is stationary and it doesn't move with the segments. So what happens is you want to sink that into your stripper plate. And we give you some examples of this here. What happens is, and we ran into this before, we didn't check their designs. They went out and built it, and the part actually, when the segments collapsed, the part went in with it. And the undercut was real big, and when they ejected it forward, it caused some damage to the segment besides the part that was destroyed. And we had to replace the segments because we're not able to chase the threads, to clean it all up again. So, so this is why we actually, I wanted to put the slide in here. So for you designers, this is something to think about. Also, as you can see on the left side, we split it on top of a radius. That radius will still allow that part to flow inward. So that's why we want you to put it into, sink it deeper basically, so you have a straight wall to help retain it.
So you're just
Okay.
making sure it's centered on the collapsible core. So when when you start your action, right, it's not going to be collapsed with the segments into the collapsible core itself. It stays stationary and centered, and the segments collapse into the center and clear all your thread. Correct?
Correct.
Okay. This is a really good feature. Thank you.
Yeah, and if you guys purchase a collapsible core from us, we'll check your designs at no cost to make sure the functionality is correct, and everything. So we offer that as a free service to you guys to make sure everything is good.
Do you also
So
help with thread styles as well, like the ending and beginning and how the thread should be molded?
yeah, I have some slides. I'll show you that
Okay.
a little bit farther down the presentation. Okay, so we're going to go to our next videos. There's going to be 2 here, and we're going to run the DuraCore, the S-Core here, and we have another one that we're just launching that is pretty exciting, and we'll show you both videos, and then we'll discuss it after the videos. So. Okay, so I got a few parts to show you and some things that we've done in the past, so we could talk about it. In this slide, it's a standard core. Some of the things about our cores are on the very top of the cores, where the segments come in. We don't have gaps in there, so that, you know, there's no clearance openings between there to show between the segments. So when the core closes, there's no openings or anything, so there's no way to get plastic down through the tops of it. And you can see this core itself, the way it's designed. When the core is completely closed, the bottom is flat. It makes it easier to put water in. Next slide. Okay, so you saw this in the video. This is a 6 millimeter diameter collapsible core. This is the smallest collapsible core that's on the market today. The thing about this core is it has an interrupted thread. So when we make cores this small, we have to make a double set of small segments so we can grind everything through, and then we replace them with the other set of segments in there so that we can do the skip tooth. We have to do that because of it's so small that the threads will, the segments on the small threads will get damaged. So this is why we do this on these small ones. Next slide, please. Okay. So what we wanted to show you is that we can do different geometric shapes on our collapsible cores. We've done rectangles, you know, oblong shapes, round shapes. And sometimes we have to achieve a final shape, we have to change the shape of the core. So when it shrinks, it goes into the correct shape required. So we don't do just rounds here. We can do all different stuff, sizes and styles. Next slide, please. What I wanted to show you here is that we created an O-ring slot in this core here. Next slide. Okay. So let's see here. Okay, so as you can see on the dome here, it has a snap feature, and the customer didn't want to move the parting line up above the radius on the part. So we had them change the part and add some standoffs on the bottom. You could see them in the picture on the bottom left, so that it will retain that part in position when the core collapses. Next slide, please. Another standard core, we just telescope the top. So if you look at it, it needed a chamfer on the inside, so we ground that right into the top of the core itself. Then they telescoped in from the cavity side. Okay, the next slide, please. Okay, so this is the two-stage collapsible core that we used in our video. We can do larger undercuts. Again, it depends on the parameters, you know, the diameters, the length of the undercut, and the depth of the undercut. Most standard cores can only do about 13%. That's pretty much across the board on anyone's collapsible cores throughout the industry. This one here is 16.2%. The largest undercut we've done was 23%. You know, and so, you know, the two-stage cores, they open up a lot more possibilities for larger undercuts. And this can be used on other geometric shapes besides round. We can do, you know, rectangles, squares, and different shapes like that. Next slide, please. I went through this earlier on the DuraCore, but I put it in here because you can download these slides after the webinar. So I just wanted to make sure that it was in both slide presentations. Next slide. So can you go up one, please? One more. So this is our S-core base that we developed. As you can see, there's no ejector box on it. It's not required on this. This creates the base is smaller. And in fact, on this base, we had to add a spacer plate between the bottom clamp plate and the support plate because we couldn't hit minimum shut height for the press. So, excuse me. So if you need, let's say if your part requires ejector pins, you know, on bigger parts, and you're not using a stripper, that's when we actually go into building a box onto them. But most of our collapsible cores, we recommend going into some type of bases like this here. Okay, so we'll show you the sequence on the next couple slides here for it. So you can see the mold's closed. Once we open it, you notice our latch locks. Those are the ones that we designed and patented. These are our EZLs. So next slide, please. So on the first movement, we set the latch locks to maximize the maximum open of the collapsible cores. And you can see that retainer on the B plate. Notice it tops out inside the housing of our latch lock. So that's how it stops. And that's all pulled up with the latch bar that's in there. And then if you see us using on the ejection stage, we're driving that stripper plate. So all of this is tied into your machine knockouts. So we just actually pull it. It's a pretty simple process that we use on this here. And it's very reliable, easy to set these and install them. Okay, so with that, we're going to go into thread design. Okay, and we're just going to talk about this. So we get a lot of threads that they have to be adjusted when they come in, and they're difficult or almost impossible to grind. So some of them, they end up needing some type of EDM to finish them. So on this slide here, to grind the threads, we have to start the wheel in part shape. As you can see, where you'd have to start your grinding wheel in, it goes in the shut off. And at the top, you know, it just tapers off to an end. So this is very difficult for us to grind. So next slide, you'll see what we recommend. Notice that we started the threads in part shape and we ended it in part shape. So on something like this, this is the best scenario for the threads itself. Next slide. So this is okay here. The thread starts in the part shape, but it runs out through the very top of the core. What happens with this here, as it runs out, it creates a knife edge on the very top of that thread. And in those thin areas have broken off the core itself. So if we have to do this, we recommend them to go in there and grind the threads, that thin area down, so it's not such a sharp edge on the top of it. So let's go to the next slide. Again, we have to start the wheel in part shape, and you can see that it's starting in, you would have to start and shut off on the bottom. So, And again, on the top of it too, it goes to a knife edge. So this isn't a good scenario. And when we see things like this, we come back to you and do some recommendations on the threads. Next slide, please. So for that same part, as you can see, we started and we stopped the threads in part shape. There's enough beef on the top of that top thread that it won't snap or break or anything like that. So that's the best type that we can go with. Okay. All right, so that's all I have right now, guys. So I'm going to pass this off to Richard in servo-mold. So thank you, and take it away, Richard.
Thanks very much, Mike. Very interesting. So first off, I'd also like to say thank you to everybody for joining. Most appreciated. We know how busy everybody is, and to take an hour out of the working day is not always quite so easy. So again, most appreciated. I would like to start actually just by giving a very brief introduction of the company. The name servo-mold is perhaps not known by everybody. DME have been distributing for us for many years, and the company servo-mold was originally the company iMold. The company's been in existence since now 26 years, concentrating solely on electrical motion for injection molds. Changed the name from iMold to servo-mold in 2012, and it's still quite interesting as to how many people didn't get the memo. So it's servo-mold, ex-iMold, same company, same people, and concentrating on servo motion. So in this particular webinar, I want to start off just by showing a quick video. It's only a minute and a half, just to give a little example of the different options that are available with servo unscrewing. So Bill, please go ahead, start off the first video. I think this was one without music, I hope. And if so, thanks, Mark. So hopefully everyone can hear me now. I shan't say a huge amount over this. It's quite self-explanatory. 2K injection mold, hard and soft. All the motions in this mold are electric, controlled by our own servo equipment, servo hardware, and servo software. You can see here 2 components being injected. After injection, mold opens and the thread in the top half is unscrewed. Finished component is ejected. Injection runs over again our servo mold ejection units. Goes back to standard injection position. Plate moves 180 degrees, again controlled through our servo mold plate rotator. Mold closes, and both components are injected, hard and soft. After mold opening, threads are unscrewed again with the servo. Through a gearbox, no belt drive on this particular version. There are options with belts, there are options with gearboxes. Threads move back to the usual position, standard molding position. Index plate rotates again, 180 degrees, mold closes, and the whole cycle starts all over again. This video is available on YouTube, and of course, there's a link to this on the sidebar. This has nothing to do with us. So back to our presentation. Why go with servo controllers, servo-controlled motion? We all know the main challenges faced with the traditional way of unscrewing or having any sort of motion within a mold. Originally was hydraulic. Hydraulics tend to have certain challenges or disadvantages in comparison to electric. Limited control and traceability being one of them. Traceability as in how many shots have I made and what exactly is going on. A shot counter will tell you how many times the mold is open and closed, but it won't necessarily tell you what your servo motor has been doing. This should be knowledgeable to everybody, really, that hydraulic and pneumatic uses a lot more electricity or energy than electric. electric motion, you're only using electricity when the motor is actually running, whilst the rest of the mold sequence is happening, you're using no power. Whereas with hydraulics, of course, you've got a hydraulic pump running all the time. Talking about the hydraulic pumps, these are usually not allowed in clean rooms. So you get clean room contamination, you're getting pressure drops, you've got very high pressure, it's loud, and there's the possibility of oil leaking, causing dirt. Within a clean room, obviously not allowed whatsoever. Many companies will in fact have to shut down a factory if there is a big oil leak. No molding would be allowed to happen, and a lot of production can be lost. So that's the main challenges with hydraulics. Please move on to the next page. The next slide, the servo solution. So here we are, full control and traceability. There's a nice little picture there of an 8-cavity unscrewing cold half. You can see where the motor is fitted nice and tidy, horizontally against the back plate. Low energy consumption, as I mentioned earlier, as a compact tool setup. In comparison to hydraulics, you don't need a great big hydraulic cylinder and a big tooth rack. I'll get to advantage or retrofit possibilities with that later in the talk. We've got no oil, obviously. It's safe to operate. There's no oil going to be coming out at high pressures. It's clean and clean room suitability, giving you high availability. You're not breaking down, you're not cleaning up. Molds will run for a lot longer during your production hours. So moving to the next slide. The thing with electrics and servos, it's been around for a long time. Many mold makers have been in the industry, myself a while, and we've all obviously seen homegrown systems. There are some very good systems on the market where mold makers have designed their own unscrewing or linear or any sort of servo motion control within a mold. The problem with this is it's a unique solution. It's not standardized. And nowadays, with globalization, the way larger OEMs are moving their molds around, a mold that could be manufactured perhaps in America would be running in Europe for tests and then move over to Asia for production. And with this sort of global availability, a single unique system does have its challenges. Spare parts, availability, support, maintenance, even in commissioning for these systems can then be a challenge. We at Servomold have standardized most of the products. I say most on purpose because obviously cores, they're always individual. A threaded core will always be in the threaded area individual to that unique application due to the plastics being used, the shrinkages, which are caused then by the plastics or given by those plastics, different resins, they have to be unique. But otherwise, motors, gearboxes, all the ancillaries that go with it are standardized, such as imagine a very large box of Lego. So moving on to the next slide, talking of standardization, the offerings that Servomold now have, I'm going to concentrate today specifically on unscrewing devices. That's the theme for this webinar. There are many other things that Servomold have been developed and manufacturing, as well as the rotary units, which we saw in the very first video, linear actuators, special solutions, accessories. But I want to talk about unscrewing devices. In the far left-hand section, you'll see components for unscrewing devices. This is when a mold maker who has already designed his mold or is in the process of designing the mold would want to have individual solution. The communication has to be at the very, very early stage with ourselves, and we can then give the full service, which you can see in the blue box in the middle. Once an RFQ has been placed or interest in the system has been shown, we would offer our service to calculate exactly what sort of motor would be needed, what sort of layout would be needed, the pitches that would be available. And we would then recommend within our quotation exactly what you would be getting. It's not possible for us to just on the top of our head say, oh, 12 cavity, 8mm unscrewing device, that pitch, what would it cost? We need to know exactly what the resins are, exactly what the complete environment is going to be for those parts so that we can calculate accurately and safely the most optimum solution and motor size that would be required. However, there is the possibility of a plug and play unscrewing device. As I mentioned earlier, the cores obviously are going to be individual, but there is the possibility of a plug and play system that is easily fitted to your mold. We pass out 3D dimensions or 3D files of these units, and they're in single, twin, triple, quadruple systems for inline or in a quadrant. The options are quite large. I do show a couple of slides later with a little more detail on that. You can see the sort of options that are available. There are drive units, obviously, for retrofitting. Retrofitting is a subject that we can also touch in a little bit later without going into too much detail. If a mold is already set, you've got your mold, it's been running hydraulic, got a great big hydraulic cylinder on the top, you want to move it into a clean room, or you just want to be more efficient, cleaner, retrofits can be made. You can see at the very top, actually, it says linear activators, but it's also the possibility of having a motor on the top of your mold instead of a hydraulic cylinder. And we have our own drive units, either at 90 degrees fitting or directly in place of the hydraulic cylinder. And of course, last but not least, for unscrewing halves, becoming more and more popular as time goes on, is a complete unscrewing half, where once we have exactly the design requirement from yourselves, we would build the complete cold half. Nowadays, it is becoming more popular, particularly in Europe, where a mold maker would manufacture himself only molding components, the actual components making the mold. Hot half from a hot half supplier. I could mention one, but I think we all know who we talk about. And the cold half from ourselves. But of course, this means very, very close communication, which we're always very, very keen to have at the very, very beginning of the project. Mark, please move to the next slide. As I mentioned, know-how and support. This is something where we really need to be involved with you as early as possible. One small side note, Mike mentioned this to me yesterday. In this particular picture, you see some cores which are hollow. And these are sleeved cores, where the core in the center needed to be stationary for a different function or a different profile, and the threaded sleeve needed to be in that sort of design. So you can see it's also possible to have unscrewing of a cap where the center core needed to be formed separately. But what I wanted to mention on this particular slide is the know-how and support, as I mentioned earlier. After an initial RFQ, we would calculate all the required forces, and we would make a custom layout and propose that within the quotation. Once that has been reviewed and discussed, obviously there's usually a little bit of discussion and advice from ourselves, requirements made by the mold maker. And if we're in a situation where the purchase order would be sent out, we would then send a concept proposal in more detail. And when after acceptance from the customer says, yes, that's exactly what I want, these are the dimensions what we want, please keep in mind, we're manufacturing the actual threaded core. So it's important that we are making the exact size, thread, pitch that the customer is requiring. And from that time on, after acceptance signature, the lead time would start. So moving on now to the next. Yes, I have a video. I'd forgotten there was a video. Brilliant. But this is a, we call it an SAD. This is a twin standard unit for noticed I've been muted, so you missed all the unbelievable information I've just been saying. I'll talk about this then afterwards. It's a twin unscrewing device. There's the motor, and the way the gears are fitted with the bearings that was shown earlier. These are the lead nuts, or lead screws. I'll explain that in a little more detail on the next slide. In the meantime, I'll let you enjoy the rather nice rendering. Here we have rotational core tubes. Also from our product, is a product that we supply. Caged roller ball bearings. We'll now show through that top plate and you'll see the little gearbox that's fitted. This is a standard gearbox. All these parts are as spares available on the shelf. So thanks for that, Mark. Sorry about not being on mute there. You missed all the really important bits, but no secrets. So what we were showing there, actually at the very top of this particular slide, is fast and powerful rotary and linear movements. As I mentioned earlier, there is the possibility of having a retrofit. On the right-hand side, you'll see a motor that's fitted there with a ball screw, which would actually take the place of a hydraulic cylinder and can be used to move your toothed rack. That's an easy option when the mold is already in manufacture or already in production and you want to retrofit to electric. But what was shown in the last video with these cores, where you can see here a side view of the core with the caged ball bearings, we're giving an accuracy guarantee of less than 1/100th of a millimeter in the length. This is extremely important when that core is shutting off up against a mold surface, cavity surface, where it's a through thread. We're also guaranteeing less than 3/100ths in radial tolerance, or I don't know what you call that in English, sorry, radial displacement. Please move on to the next slide. I think I can show a little bit more of what we're talking about here. When you look at this a little more in detail, this is our patented system. It's been patented many, many years ago. And a traditional unscrewing core would have a gear halfway down or 3/4 of the way down, thread at the end. Maybe you'll cool it if you can. It might have a coated surface area, but that would be about it as far as bearings are concerned. Now, what we've done is taken the actual motion of the core, which goes through that gear. The gear on the far left, it's got 2 little red arrows. That's actually held in position with these roller bearings. Those roller bearings take all the lateral force, radial force as well, but it's the side force of the gearbox pushing against it, which can usually cause premature failure of the core, or at least you'll start getting burrs as you'll get wear and tear in the diameter of the core running up and down inside the cavity. We eliminate that by having this gear, which is fitted against the splines on the back of the core. These splines also have the lead nut or lead thread. There's the bronze colored lead nut fitted to it. That's held in place by that black plate, keeping still. And as the gear turns, then of course the threaded core rotates in whichever direction you're turning it in and moves the core without any sidewards pressure. Basically, in a nutshell, we're eliminating any sideways motion and letting the core turn freely, causing far, far less wear and tear. The end of the cores, as an option, can be DLC coated on that sealing surface. We recommend it, and 9 times out of 10, it's also taken. So moving on, Mark, to the next slide, I wanted to show a few examples. On the left, got 5 individually controlled threads. There are, believe it or not, 5 different threads. They were all different sizes, different pitches, different diameters. Of course, there you have the possibility then with individual motors. These motors come in different sizes. There's extra small, there's medium, large, and extra large. To get a little bit of an idea, you can't really see it here in scale, of course, but the side threads, they were small motors. In the middle, and these are individual devices. There's nothing standard here other than all the units that we're using. Obviously, all the gears, all the gear wheels, the bearings, these are all standard parts. This is an 8-threaded gear-driven system for a cold half motor. We only supplied what you exactly see there. Interestingly enough, and I won't go into detail about that, but this is an option which I'm sure DMA would be able to support you with, are the internal cooling cores, rotational cooling tubes. To the far right, we have a 36-threaded gear driven with 2 motors for a medical application, a lower lock application. Again, all with gears. There's option now and then of belts, depending on the requirements, depending on the clean room requirements needed. Moving to the next slide. These are what you saw in the video earlier. You've got your double standard unscrewing unit. There's also a single, there's a triple, and there's a quadruple standard core, unscrewing core device. Moving on. The same standard devices, actually all of the ones that we've shown before, can also be activated from the side. If there isn't enough room at the top of the mold or behind the mold or underneath the mold, the positioning of the actual motor is totally flexible. We have gearboxes which can be fitted at all different positions. We have threads coming in at all different angles. This is a standard unit using motors fitted to the side of the mold. And then last but very not least, the very last page is our control units. Obviously, these motors are all very nice, but we also need to be able to control them. And we have brought out, very proud to show that we brought out last year, our new control unit, the SMC. So you can see in the picture here, at the very bottom, you have your touch screen. We brought it up to the new age, brought it into the 21st century. It's touch screen. It's completely on the fly adjustable. You have RFID user access, meaning that those who are allowed to adjust can get an RFID chip. That's also recorded, of course. We can see who opened what and who adjusted what. This is also very, very important, particularly in the medical industry, where molding processes are set standard and sealed, and adjustments are quite frowned upon where not necessary. We have the boxes. You've got the SMC Mini, the standard, and the rack. Within these boxes, you have different servo amplifiers. Of course, the larger the motor, the larger the amplifier needs to be, and that's all selectable, which is why we need to be able to be in at the project early so we can recommend which motors to be used. It usually then isn't a case if a wrong motor has been chosen earlier by another supplier, of course, it isn't a simple thing of just changing over a motor. You need to change over then the amplifier. These control units are not to be underestimated. It isn't an empty box. There's a lot going on in there. Every single card has its own mini computer. And the mini SMC will control one motor. The SMC standard control up to 4 drives. You can have 2 or 3. And each drive has its own price, but it would go inside an SMC standard. And then there's our SMC rack, which would take up to 8 drives. When required, we work together with the company Fella, who have been in the industry of temperature control units since many, many years. They're quite near to us in Germany. And we can supply a hot runner controller and a servo controller within the one rack, sharing the same screen. So that brings me to the end of my presentation. I think I've hit my 20 minutes, perhaps a little bit longer, hopefully not. And I hope it's been interesting for everybody. And please feel free. I know Michael will now bring us into questions and answers, and we'll all be here happy to answer any questions you may have. Thank you.
Yes, nice job. Thank you very much for staying on time there.
I just realized I didn't put my camera on. Nobody saw me, but no worries. Okay. You didn't miss out on anything.
We were interested in the good images and the PowerPoint, so it was good. I got a couple questions here on servo. How many motors can we control with one controller?
Yep. Well, as mentioned in the very last slide, We have the SMC Mini will control only one. When a second motor is needed, one would have to go up to the SMC standard. So it's good to keep in mind that if you think you might be controlling more than one at a later stage, it's best to purchase the SMC standard. What is also quite interesting is that the SMC controllers are flexible. You can program up to 99 programs within one controller. If you have molds that don't run 24/7 all the way through the year, and you have several different molds with servos in it, then of course you can have a different program number, but use the same controller. You only need to buy one controller. Hope that answered the question, Mike.
Yep, I believe so. Yep. Let's see, at what angles can the unscrewing cores be positioned in a mold?
We're totally open for that. We have systems for fluid control companies where units have had threads coming in at a 20-degree angle or a 45-degree angle or all such different angles. We've even had systems where the threads have to meet each other at different angles. So and then moved obviously then with a linear. It's pretty well unlimited as to exactly at what angle these threads need to come into in the mold. It's the mold designer's limitations at the end of the day.
Okay, very good. Mike Raymond, what is the smallest size collapsible core that you can offer?
6 millimeters is the smallest that we can offer currently.
Okay, and then are there coatings available for glass filled or abrasive resins?
Yes, usually we DLC coat them. You know, if you have like PVC or something that's sticky material, we can DLC coat the segments and the center guide system. We at least recommend the center guide system because it doubles your warranty when we DLC coat at least the center guide. So it goes from 500,000 cycles to 1 million cycles when we DLC coat them.
Okay, great. And then what type of base material are you using for those?
The segments are made out of 420 stainless. We heat treat them to 52 to 54 Rockwell, and the center guide is H13, and that's treated from 48 to 52 Rockwell.
Okay, great. Just one question here. How is the design done? Question mark. Is all the unscrewing part pre-designed? And I'm not sure if that's got to be for servo, I would assume.
Yeah, I was just thinking about exactly what we're asking here.
Yeah.
I mean, usually a customer or the OEM would have a particular requirement. They would say, yeah, I need an M8 times 1.25, and then we would be given the exact resin type, and we can calculate then out the shrinkage required, the shrinkage that would be given with that resin, and with that information, we would then design ourselves the core and the thread on that core.
Okay, great.
That would be ourselves. The toolmaker doesn't need to give us that design.
Mm-hmm. Yeah, and I
But
think
of course, we need the design of the part.
Right. Yeah, and I think obviously both options have had quite a bit of background, and we can help with design questions and help find the right answer for the designer if needed. What is the maximum minimum number of threaded cores possible? And I believe this is a servo question.
The maximum number of threaded cores possible.
Mm-hmm.
Well, I think it would really depend how big the mold you want to go. Spacing could be a limitation, depending on what sort of pitching you're going to be wanting. It would depend on the size. Because if it's a 50 millimeter thread, we're not going to be having 128 of them unless you have a massive machine and a massive mold. But at the end of the day, I wouldn't say that there's a specific limit of number. One can have several racks, one can have many servo motors fitted to the mold. It really comes down to the requirements of the mold maker and, more importantly, the end user. how many parts do we want to produce per year, how big is the mold going to be, what machine are we going to put it in, then we would be able to see what is actually possible. So it would be on a case-to-case situation where one would be able to define how many cores can be made. But a 64 cavity for unscrewing lure lock, for example, is easily realized.
Okay. Is there a battery backup system from Servo for the any plant power losses?
Oh, that's quite a question. I have to be honest. I can't actually answer that. For what exactly? For the controller? I do believe that the controller does have its own backup, but only as an emergency. It wouldn't be running. I mean, yeah. If there was a power cut, literally during the middle of production, which I could, to be honest, I've never ever heard of that happening. Wow, I mean, a factory being shut down with power during production would be pretty tragic, actually. I think that the least worries you're going to have is whether our controller's running or not.
There's one other question here, actually two more. For Servomold, customers asking, they need like a ballpark pricing, what we call like a rough estimate of quotes, because hundreds of molds every year, and they're not quite sure if we want to go through all of the finite details to get a firm price on every application. Is there ballpark type quoting?
That is fair. Yeah, I mean, if a customer really is not just requiring quotes for hundreds of molds per year, but it really is building hundreds of molds per year, and one knows, okay, the mold sizes are going to be like this usually. I mean, a mold maker wouldn't be making 100 completely different molds. I can imagine that, I mean, we have customers that are usually making a particular type of part. This is what they're specializing in. I don't know, let's say milk bottle tops or whatever. And this is the range that we're working in. Our caps are usually 20 millimeters to 35 millimeters, and that's it. And we know that in advance. Then, of course, we can sit down together and work out a sort of a grouping and say, yes, for those sort of sizes, for that resins that you're currently using, then a ballpark price for a group of molds can be made. But there we need really open, transparent communication for us to be able to work on that. Okay. There's just basically the reason that we sometimes hold back is we want to be on the safe side. The last thing we want to do is quote something without full transparency and full knowledge of what you're requiring, and then end up recommending something that isn't ideal. That nobody would be served with that. But ballpark pricing can definitely be done like that, yes.
Okay. Let's see here. Another pricing question, rough estimate for the Servo single drive off the shelf unit with controller. What is approximately the MSRP for that? I mean, over a webinar, I would rather not speak of specific prices. I don't think that would be. That's okay. So what we can do is we will be sending out contact information. Exactly. Yeah. Reach out to us and we can address your question at that time. Without a doubt. Thank you. Yep, no problem. Okay, good. And of course, thank you very much for asking. Whoever sent the question, more than happy to help out. Sure. Okay, I think we have a couple more questions if people want to hold on. One or two more here for collapsible cores. How do you put the detail into the cores?
We either grind it or we'll set it up on a 5-axis and do the machining. Depending on the cores, like the S cores, we always create a fixture for each core. And in fact, we can send those fixtures to the customers because they end up piling up for, so they're all custom made for each core. But either we grind the threads, or in some instances, we have to go back in and depending on what we're putting on it, we 5-axis CNC them.
Okay, good. And then one more question, can you make collapsible cores for high temperature resins, for thermal resins?
Yes, we do. So we've done them for Altem, and instead of using the 420 stainless segments, we go to DC53, and because it can handle high temperatures without annealing. So that's what we do when we go into high temperature applications.
Got it. Okay. How close can we put the collapsible cores together?
That depends on the size. The DuraCores, seeing that they're in a round shape, we can tuck them in close together. And in the S-cores, we can actually put them in the same set of plates and bring them in close. So we've done that quite a bit. So we can tuck them in, depending on the size, like I said, we can put them side by side, probably within 5 millimeters of each other.
Okay, great. Okay, well, good. That completes all the questions. And I just want to thank the presenters, Mike and Richard, for putting that together for us. And again, we in the chat section, there are some handouts. If you open up the right there, you can see the handouts. We will send out links to this presentation so you can review it. There's a lot of information on our website as well at dme.net on all of these products. And don't be afraid to reach out to us and we can help you out with your application.
Thank you very much, Mike. Been a pleasure, and thank you everybody for listening.
Thanks for joining.
Some of you again.
Thanks, Richard.
Thank you.
Have a good day. Bye-bye.
And yourselves.
Bye, everyone.
Goodbye.